am Megumi Enomoto from Atmosphere and Ocean Research Institute, the University of Tokyo, Japan. I am talking about my study which estimates vertical habitat changes of juvenile Japanese jack merkel by outlet microchemistry. First, I introduce Japanese jack merkel. Japanese jack merkel, Tracus japonicus, is one of the most important fishery species in Japan. FAO showed that the total global catch of this species was around 200,000 tons for recent 10 years. Their main spawning ground is located about northeastern area of Taiwan in the East China Sea. They show the unique life history trait. When juveniles reach around 14 mm standard length, they tend to switch their habitat layer from the surface 10 to 30 meter depth to semi-demersal layer 70 to 140 meters depth. In addition, they have 3 life history traits other than habitat layer change, HSC. Japanese jack merkel larvae starts metamorphosis to juveniles. Behavior change to self-swimming from flotsam such as drifted algae or jellyfish, and swimming ability increase. However, when they change the habitat layer and which treat effects of HLC has not been clarified. It is important to know about HLC since the abundance of demersal juveniles after HLC is related to the abundance of recruitment. Therefore, we aim to understand when juveniles start habitat layer change. How long do juveniles spend HLC and which traits relate to HLC? To investigate this, we use outlet and outlet microchemistry. Outlet is biomineralized in organic carbonate in the inner ear of fish. Outlets increase in size concentrically and are formed daily, which are called daily rings. The outlet growth increment of Japanese jack merkel has linear correlation to their standard length. In addition, the secondary premedier, which are the structure like the core of outlets, are formed in outlets of Japanese jack merkel. The date of first secondary premedium formation, SPF, in outlet shows the start of metamorphosis from larva to juvenile of Japanese jack merkel. Next, we are talking about outlet microchemistry. Outlet oxygen stable isotope, delta OA10 outlet, reflects experienced water temperature and salinity, delta OA10 of seawater by fish. If fish undergo environment at lower temperature and higher salinity, which is a feature of semi-immersion layer in ECS, delta OA10 will increase. Outlet worm micromills use a high-precision micromilling system, which consists of the computer and micromilling dial, and enable us to mill specified area on the digital picture automatically with high precision. Here is a monitor of the computer which shows digital pictures of outlet and the stage of micromilling area via microscope. This is an outlet powder which is analyzed, and the drill. Recently, this technique, which will enable us to analyze outlets at higher resolution, with 10 daily links in outlets on Japanese sardine, were developed. Using this, we think the signal of HLC timing can be detected. In this study, we micrometer outlets at this resolution. From the core to the increment at 20 daily age, which means first 20 daily age segment, every 5 or 10 increments at marginal segment between the core segment and the edge segment, and 5 to 7 daily age segments at the edge segment. The outlet samples were provided by Seikai National Fisheries Research Institute, Japanese Fisheries Research and Education Agency, of which daily outlet increments were analyzed in previous study. This figure is a sampling point in East China Sea, which are divided into 3 areas latitudinally. In central area, we use samples from 3 years 2005, 2008, and 2009. This table shows the sample size. Since there were no significant differences of HLC timing among area and year, our results below were analyzed using average for all samples analyzed. In this study, HLC timing were estimated by 2 types of indices. HLC moment was defined as the index to detect the signal which fish change their habitat in the short scale, and HLC duration was defined as the index to detect the signal which fish change their habitat in the long scale, which was larger than micrometer segment. First, the HLC moment is based on the highest delta OA10 outlet gap signal. Here is an example of samples analyzed. X-axis shows the daily age, and Y-axis shows the delta OA10 outlet. Wedges test was conducted before and after of each boundary of each micrometer segment, dotted line, in the time series of delta OA10 outlets. The segment boundary, which shows the significant difference, and the largest difference of the delta OA10 outlet in the time series, was defined the HLC moment as the central daily age between just before and after segment on the boundary. Second, HLC duration is characterized by gradual delta OA10 outlet change. HLC duration was defined as the duration that delta OA10 outlet value increased from the minimum to maximum across the HLC moment in the time series. Then, we consider the life history trait of Japanese jerk merkel in order to compare HLC. First, to know the growth rate, standard length at each daily age, and daily growth rate of standard length were calculated using the biological intercept method. Then, the daily age of the maximum growth rate was determined based on the daily growth rate. Next, daily ages of 3 trees were recalculated. Start of metamorphosis from larvae to juveniles is related to the date of first secondary primitive formation (SPF) in otoliths. Then, juveniles start behavior change to start swimming from float zone when their sternal length becomes larger than 20 mm. Their swimming ability increases when they become more than 30 mm in total length. Therefore, the date of SPF, daily age at 20 mm and 30 mm were considered as the start date of each 3 trees. Here is the result of comparison among HLC and life history trees. Y-axis shows the life history trees and HLC timing including HLC moment and duration, and X-axis shows daily age. First, daily age of 3 trees were different significantly. Metamorphosis started 28 daily age, said swimming from float zone started at 35 daily age, and swimming ability increased at 43 daily age. Next, HLC moment was 42 daily age. HLC duration started 28 daily age, and after 28 days, HLC duration ended at 56 daily age. Then, we compare among HLC and life history traits. Start of metamorphosis was not significantly different from start of HLC duration. Also, the daily age of swimming ability increase, HLC moment, and max growth rate had no significant difference. Therefore, they indicate that fish start HLC after metamorphosis start and after increasing swimming ability, signal of HLC increases. Next, we compared water temperature variances by HLC and life history traits. To know that, we calculated the correlation between water temperature and delta O18. By using delta O18 otolith value at age segment, correlation between delta O18 seawater and salinity at ECS from previous study, and water temperature and salinity in the layer fish samples code. Here is the equation between water temperature and delta O18. Here is the result of comparison of water temperature variances between before and after HLC, life history traits, and observed difference from the surface layer 10, 20, and 30 meters depth to the bottom. First, the difference before and after HLC moment was smaller than that from 30 meters depth to the bottom. However, the difference between before and after HLC duration was similar to that from 30 meters depth to the bottom. It indicates that HLC duration reflected temperature difference before and after HLC. Next, there were no significant difference of temperature differences among life history trees. Therefore, juveniles gradually change habitat layer, not suddenly after specific treat. Here is the conclusion. We found that Japanese Jack-Merkel juveniles change habitat layer gradually for about 28 days. Also, they start to change the habitat layer when larvae metamorphose juveniles. In future works, more accurate temperature data awaiting correlation by rearing experiment should be calculated. In addition, direct factors which causes HLC such as diet should be detected. Thank you for your listening.